last session, we have seen how to compare EMF of two cells by using sum and difference method. So, in this session, we will see how to find the internal resistance of a cell. So, this is the circuit diagram to find the internal resistance of a cell. So, in this circuit diagram, it consists of a potentiometer wire AB. Okay, this is the potentiometer wire AB, which is connected in series with this driving battery of EMF E, key K, and the rheostat. Okay, this potentiometer wire AB is connected in series with this driving battery of EMF E, key K, and the rheostat, where this terminal A is at higher potential than this terminal B, and a cell of EMF E1 whose internal resistance is R is to be determined is connected across this potentiometer wire AB. Okay, a cell of EMF E1 whose internal resistance is R is to be determined is connected across this potentiometer wire AB through this galvanometer. Okay, and this galvanometer is used to measure the electric current. The other end of this galvanometer is connected to this jockey, and this jockey is used to achieve the null point where galvanometer shows no deflection. Okay, now this resistance box is connected across this cell of EMF E1 with this key K1. Okay, this resistance box is connected across the cell of EMF E1 with this key K1. So, this is the construction of our circuit diagram. Now, we will see how to find the internal resistance, that is small r of the cell. So, there are two cases. First case is key K is closed, this one. So, this key K is closed and key K1 is open. So, this key K1 is open. When this key K is closed, that means current flows through this driving battery, this potentiometer wire, galvanometer, and this cell. Okay, when this key K is closed, that means current flows through this driving battery, this potentiometer wire, galvanometer, and this cell of EMF E1. Now achieve the null point with the help of this jockey. This null point is achieved at point C, and the distance between null point and the terminal point A is L1. Okay, the distance between terminal A and the null point is L1, and this L1 is the length, or it is the balancing length for this cell. Okay, this length L1 is the balancing length for this cell E1. When we achieve the null point, that means galvanometer shows no deflection, or the value of current is equal to 0. When no current is flowing through this galvanometer, that means the potential difference across this balancing length is equal to potential difference across this cell. Okay, the potential difference across this balancing length, that is L1, is equal to potential difference across this cell. So, potential difference across this cell is equal to E1, and potential difference across this balancing length is K into L1. So, the potential difference across this cell is E1 is equal to potential difference across this balancing length is equal to K into L1. This K is nothing but the potential gradient. That means the potential difference per unit length of the wire. So, this is your equation number 1. Hence, when this key K is closed and this key K1 is open, we get the first equation as E1 is equal to K into L1. Now the second case is when both the keys K and K1 are closed. So the current flows through this driving battery, potentiometer wire AB, this cell of EMF E1, galvanometer, and the resistance box. That means current flows through this complementary circuit for the second case. Now achieve the null point with the help of this jockey. the null point is obtained at J dash and the distance between terminal A and the null point is L2. This L2 is nothing but the balancing length. When we achieve the null point, that means this galvanometer shows no deflection and value of current I is equal to 0. Even though we achieve the null point, in this case some amount of current is flowing through this complementary circuit. Okay, even though we achieve the null point, some amount of current is flowing through this complementary circuit, and because of that the potential difference across this balancing length L2 is not corresponds to EMF of the cell. Instead of that, it corresponds to terminal voltage of the cell. Why? Because some amount of current is flowing through this complementary circuit. Hence, the potential difference across this balancing length L2 is not corresponds to EMF of the source. Instead of that, it corresponds to terminal voltage of the cell. Hence, for the second case, we get the equation as terminal voltage V is equal to potential difference across this length is K into L2. Hence, we can write the second equation as V is equal to K into L2. This is your equation number 2, where this K is nothing but the potential gradient. Now from this equation number 1 and 2, we can write from equation 1 and 2, we can write E1 upon V is equal to KL1 upon K into L2. Now this K will cancel and we get the equation as E1 upon V is equal to L1 upon L2. This is your equation number 3. Now consider the loop P, Q, S, T, P. Now consider the loop P, Q, S, T, P. For this loop, applying Kirchhoff's second law, that is voltage law. Okay, when we applying Kirchhoff's second law for the loop P, Q, S, T, P, then EMF of the source becomes negative because we are tracing the EMF of the source from positive terminal to negative terminal. Okay, hence the first term of EMF is minus of E1. Now here the potential difference is, now well, the direction of current is from Q to P and we are traveling from P to Q. Hence directions are opposite. Hence here we get term potential difference as a positive, that is plus I into R. Now we are traveling from S to T. So, and the direction of current is T to S. Here also directions are opposite. Hence here we get also positive potential difference. Hence here plus I into capital R is equal to 0. This small r is the internal resistance of the cell and this capital R is the external resistance of the cell. Now from this equation we can write E1 is equal to IR, that is internal resistance, plus I into capital R. But we know that V is equal to I into capital R, that is potential difference is equal to I into R. So from above these two equations we can write E1 upon V is equal to I into small r plus I into capital R upon V is equal to I R. Now E1 upon V is equal to, take I as a common, so we get I into R plus capital R upon I R. Okay, so now this I get cancelled and we get the equation as R plus capital R upon this R. So E1 upon V is equal to small r plus capital R, that is internal resistance plus external resistance upon this R, and this is your equation number 4. Okay, this is your equation number 4. Now equation number 3 and 4, from these two equations, from equation 3 and 4 we can write the LHS of both the equations are same. Now compare RHS of the equation 3 and 4. Hence we can write L1 upon L2 is equal to this small r plus capital R upon capital R. Now we have to find internal resistance of the cell. So L1 upon L2 is equal to R upon this capital R plus this R upon R. So we get here R plus R plus 1. Okay. Now here we have to find internal resistance small r. Hence small r is equal to L1 upon L2. This plus 1 here becomes minus L1 upon L2 minus 1 into this capital R. Okay. So finally we get the equation for internal resistance of the cell small r is equal to L1 upon L2 minus 1 into capital R, that is the value of resistance box which is selected.